Okay. All right. So I can say things, but I'm not hearing anything from the room, I don't think.
Do you have a timer or do I
Ah,
need to yell at you?
I can hear you now.
But do I need to yell at you or do you have a clock?
I have a clock.
Okay. 15 minutes, 12 minutes to talk, and about 3 minutes for changeover and all that. You know how it goes.
Yes. Yep.
Okay. Welcome back to, oh gosh, what is it? Oh, the afternoon, session 3. And since Dirk insisted on titling his session, this is the session on how to collect more data than an army of graduate students and undergraduates could ever possibly analyze in their lifetime. So our first speaker today is going to be Nathan Delane from University of Northern Kentucky. He couldn't drive all the way across the river to come here.
It's so
Oh,
far.
Northern Kentucky. He broke his what? Neck?
Leg.
Oh, leg.
Leg. Yes. I would be there, but
he's moving pretty well
I'm
for a broken
currently
neck.
15,
Anyway,
15 miles away. Yeah.
Nathan is at Northern Kentucky University, home of the Norse,
Yes, correct.
who made the NCAA almost tournament, sort of kind of this year.
I have no idea.
They didn't. Anyway, Nathan is going to talk to us about, he's been a longtime collaborator with the Sloan Digital Sky Survey, and he's going to talk to us about some of the plans that SDSS has for after Sloan 5. So Nathan?
All right. Thank you very much. So yeah, I'm going to talk a little bit about sort of the next steps in the Sloan Foundation. To get us started, SDSS has been going now for a very long time since the collecting data since the 2000 and building before that. And in SDSS 1 and 2, we showed that we could do both photometry and optical spectroscopy. By SDSS 3 and 4, we started doing infrared spectroscopy and using IFU systems. And then SDSS 5, we moved to actually using robotic positioners to be able to move our fibers around us versus using handheld systems and expanding our IFU abilities. So how do we build on what we have? Well, we've got 3 telescopes right now ready to go. We have APO in the north, our telescope at Las Campanas, and our LVM observatory, which does the IFU observations. We also have a huge hardware and software stack. So we got, our telescopes, and we've got our various pieces of observing software. We've got targeting databases. We've got strategy making software. We have a scheduling software. We have data reduction of different sorts. And then we have spectral classification on top of that. So somehow we managed to build ourselves a car, and it's time that we do something with this, right? We have this amazing ability to gather huge amounts of data. If we push the limits on this, what are we capable of pulling off? And so in AS5, what we're looking to do is to have this huge time and spatially resolved spectroscopic survey. We're going to run roughly from 2027 to 2030. And we're trying to understand the dynamic universe, understand the fundamental chemistry and dynamics of the Milky Way, especially looking at what we call, the dark side of the galaxy. And we're going to try to map stars and gas in large star formation regions across local group galaxies. And then we really want to hammer down our understanding of nucleosynthesis and how to actually get the elemental patterns that we see in the stars. So I'm going to spend a certain amount of time on the ones I know, parts of the survey I know the best, but I'm going to try to give a little bit of time everywhere. So how do we sort of set ourselves apart from sort of planned or existing surveys? Well, we have this high signal to noise, high resolution IR spectroscopy of the entire sky, right? We can do both northern and southern hemisphere. We also are going to have a large IFU system, both in the north and the south. And if we combine that with our robotic system to do both infrared spectroscopy and low res optical spectroscopy with our, with the robot system, we're able to go very quickly, make a lot of design changes. And so we can do very quick, shifts from place to place. And we can also do longer term analysis, of some objects that we've been able to get data on for now over 30 years because SDSS has been around that long. So we're breaking this down to sort of four major surveys. There's the Dynamic Universe Explorer, which I'm a survey scientist on, Hidden Galaxy Explorer, Local Volume Mapper 2, and the Atomic Genesis Explorer. And I'll deal with each of these in turn. So the Dynamic Universe Explorer is what I know the most about. It's the one I've been most deeply involved with. Sort of has three major pieces. We have the trigger program, which is meant to be a rapid response to you know, objects of interest that appear, right? These could be recent supernova or cataclysmic variables or anything that needs a quick, within 1 week, spectroscopic follow-up. And so we've been designing systems to take alerts in from the Rubin Observatory, ZTF, et cetera, and have the ability to move to a piece of sky and start to observe objects based on that. So if the trigger portion of the survey is sort of the fast response, the rhythm survey is looking at changing dynamics over longer periods of time. Here we're trying to explore things like how AGN, reverberation, changes as a function of time. We're picking up on things that we've looked at, binary systems, young stellar objects. We can do astroseismology. Again, rhythm is working on the order of days, months, even years, right? If we combine with previous data that we've taken in SDSS. But we're looking for sort of these more periodic, or at least things that are going to vary, again and again over time. It's not necessarily perfectly periodic. So the AGN, obviously, right, reverberations don't do that, but they at least continue to change over time. And then we have scope. And so whereas, rhythm and trigger both, in the case of trigger in particular, right, we have just a few objects that we're looking at. We have to fill the rest of our 500 fibers with, things that also need spectra. And so that's what scope is for, right? So this is getting like spectra to get metallicities of RL Lyra stars so that you can get decent absolute magnitudes of them. Changing look AGN, compact binaries, host galaxies of supernova. So these are things that don't need to have spectra at any given moment in time, but are getting basically characterization spectra on known variable objects. The next survey is the Hidden Galaxy Explorer. And the idea here is that if you look at the galaxy, right, in the optical, you go, there it is. Oh, look at all those dust clouds. Well, I guess we're done. Aha, but wait, we can go to the infrared, right? And in infrared, you punch through all that dust and you're able to actually see the stars behind it. And so the Apogee is a near-infrared spectrograph. We've been using it over the last 15 years, and we're going to try to push at what it's capable of doing. Up to this point, we've been able to get data. If we're basically centered on the sun here, right? Here's the galaxy behind it. And so we've done a very good job of mapping out sort of our part and a pretty decent distance out from the sun. But what we'd like to do is understand what's going on over here, right? What's on the far side of the galaxy that we can't see, right? On some level, like Artemis 2 is able to go and, or Artemis program is able to go see what's on the far side of the moon. Well, we're going to try to do the same thing, but the far side of the galaxy. So again, a place that people don't go to because there's a bunch of dust in the way. We've got infrared spectrograph, and so if we just expose long enough, we can get over 1 million red giant branch stars over on that side. So just to give a sense, here's the solar circle, right? This is the orbit that we'd be on, and we're going to be able to push out to about 15 kiloparsecs from the center of the galaxy on the far side. And so we can then ask things about the structure of the Milky Way galaxy, its disk and spiral structure. We can ask about, 3D chemistry, right? Like how are stars moving up and down over the course of their lives within, like, for instance, the disk. What does the bar of the Milky Way really look like if you are able to see the other side of it? And, generally be able to measure kinematics plus a significant number of chemical abundances, right? Depending on the type of star, we can do tens of different elements pretty well. And so you can really start to ask complex questions about the formation of stars in different parts of the galaxy. And so this just gives you a sense of how we're going to do this. So each of these little red dots is a single pointing of our telescope. And again, we have 300 infrared fibers that we can use and another 200 optical fibers on top of that. And so we're just going to tile along the galaxy, the inner part of the galaxy, and figure out what's going on. Okay. A little more quickly, I'm going to talk about the local volume mapper. So this is part 2. This is a breakdown of the sky with, or this little object with an H alpha, an O3, S2, and S3. And so we've been running the local volume mapper in the southern hemisphere in SDSS-5, and the goal for after Sloan 5 is to build a northern hemisphere facility to complement that, right? Because obviously, if you want to look at things like, for instance, the Andromeda Galaxy, you got to go to the northern hemisphere. And so, just give you a sense, right? Here in green, we have what the field of view of LVM is, and then this little circle here shows you the size of a fiber. And so, basically, what it does is it takes all the light in that little circle there and it integrates it into a spectrum. And so you just get a whole bunch of spectra, which creates your IFU. And the idea here is we just sort of work our way across the sky and you're able to get in detail, right? Spectra of what this star forming region is doing as versus that part of a star forming region, right? And we're focusing on relatively nearby objects, and so we get very good spatial resolution, right? Sometimes down to 10 parsec resolution, depending on which object we're looking at. Again, this is our R4000 spectra. And so because of this, we're going to be able to push down, to the more dwarf regime to sort of understand the interaction between stars and the interstellar medium that they were born from. And of course, because we've already done a lot of the work in the south, we're going to go back and now expose much longer, 10 times longer in the south, to be able to really pick up on the interesting regions that we've already studied there. And of course, the north, you have all new objects to work with, so that'll be exciting as well. And so again, our core objectives here is to trace the assembly history of the galactic disk and stellar populations across the local group, right? We want to understand how star formation and stellar feedback, right, changes the ISM and thus changes, the stars that we see born around us, right? Why do population 1 and 2 stars have exactly the we know in general why they have the chemical abundances that we do, but now we want to ask questions about this specific cloud or this part of this specific cloud, and we can do that here. Yeah, so very quickly, I'd also like to talk a little bit about the Atomic Genesis Explorer. This survey is still, I think, most in the planning phase because we're still looking for a high resolution spectrograph, optical spectrograph, to be able to do this work. And so the idea here is really trying to nail down our understanding of how well are we measuring, these different elements, how well do our chemical enrichment models work, right? How is binarity, right, changing the chemistries that we're seeing? And so, we have these huge data volumes, but there's still a lot of questions about how the Milky Way actually formed in detail. And this will allow us to get very high signal to noise information, and thus, actually be able to get very detailed chemical abundances that we can then connect to the abundances we're getting from Apogee, which is high-ish resolution. But this, of course, will allow us to really get into the details. And so we have a couple of different telescopes that we're thinking about partnering with as part of this. And again, the idea is to get sort of our 70,000 spectra at very high single, single noise 100, and be able to actually benchmark all the things that we've been doing so far. All right, well, if any of this sounds interesting to you, you can go to the SDSS webpage and click on the Future tab, and we talk about all these things. I think that we have a lot of new and interesting science that we're going to be able to do. We're planning hard right now. We first go on Sky on January 1st of next year. So, people we're writing SRDs, we're doing our targeting, we're collecting up targets. So if you want to be involved, now's the time to do it. Thank you very much, and I'll take questions.
Let's give them a hand. And for the people who want to join, I know money is always important at this point. Who's the contact person? Is it you or Peter Finchboy or some of the others?
Peter, I mean, I can certainly connect it to either Peter or Keith Hawkins as the director. But yeah, those, they're the ones who can tell you what's going on. I don't know if you're on any of the SDSS mailing lists, but we have sent out sort of the joining document, so you can both join SDSS 5 and After Sloan 5 at the same time right now for a new special rate. But so I can send you those basic documents, but the people that you ultimately are going to talk to are Keith and Peter.
Okay, thank you. Any questions for Nathan? You have just wowed them and amazed them.
Ooh.
Good job.
Well,
Sloan
it's the
is
traveling
a great
across the river. My magical voice is. Yes.
Wait, Bene has a question. He's clapping. Okay.
I thought it was good.
It's technology. I'm a dinosaur. Okay. Thank you, Nathan.
All righty.
So our next speaker is Mark Pitts from Eastern Kentucky University. Mark has been doing yeoman's work trying to corral teachers of undergraduates developing software to get involved with RUN, the Rubin Undergraduate Network. He volunteered to lead all discussion and has now been roped into leading a huge effort. Yeah.
All right. Hello, everybody. For those of you who don't know me, my name is Mark Pitts, and I do, in fact, hail from Eastern Kentucky University. And I'm here to talk to you about the Rubin Undergraduate Network, where our primary goal is onboarding undergraduates so that they're all ready to stick their face into the fire hose that is LSST. All right. Oop. And this one. There we go. Thank you. There we go.
And you can exit out that. Zoom is still up.
There we go. Okay. Rubin Undergraduate Network, or RUN as we like to call it, is a volunteer organization, faculty, staff, postdocs from primarily undergraduate institutions. And we were an organization that began to kind of coalesce like an interstellar cloud somewhere around 2024, about 2 years ago or so. And it essentially came from the primary motivation of the wide accessibility that the LSST is going to have. So the fact that You just need to be a US or a Chilean citizen, and you will get access to the data as it comes out on the conveyor belt, has opened up the floodgates of opportunity for smaller undergraduate institutions. And because of that, naturally, the next question comes up of, okay, now I don't need to worry so much about getting data for my students, but now how do I make sure that I'm able to correctly mentor them? For the students themselves, it's where do I start? There's a lot of challenges that come with getting started with astronomy research when you're at the undergraduate level. And this was the other impetus, was these particular challenges that are unique for these students. For example, unlike for graduate students, there's no light at the end of the tunnel where they won't be taking classes anymore when they're trying to do research at the same time. You know, they might be, they're more likely to be having to handle jobs and other employment at the same time. And if they are able to get a mentor, especially if they're not at a very R1 prestigious institution, it's maybe their mentor doesn't have either the time or as much expertise to help them out in getting started in their projects. So having access to the data is just the beginning. So we got together to find ways and brainstorm different things that we might create to help supplement and support undergraduates in their astronomy research, and or to curate what is already out there so that we're not reinventing the wheel. If there's good stuff out there, we just want to kind of put it all in one place, and we can just kind of say, okay, undergraduates over here, if you're kind of wondering where to start, there's some excellent tools to get you started. So here's just a quick smattering of several of the institutions that some of our more active members are affiliated. So here's our basic goals here. Offer guidance and support to undergraduates seeking to perform substantive research projects that involve Rubin data. So it's not, we're not casting our net quite so wide as to just say astronomy research in general. We are kind of giving ourselves a little bit of focus. It is, how do we specifically use the widely available tools for Rubin for this? Number two, provide resources and a supportive community to the mentors of undergraduates. Again, especially those that maybe either have never mentored a undergraduate before, or they're just, their time or their expertise is making them a little nervous about doing that. We want to be able to give them that support. And then pool our collective knowledge, expertise, and resources. Essentially, we're all kind of in the same boat as far as being from mostly these smaller institutions. And we want to make sure that no one is double working on something, and that we have plenty of expertise to go around. So some of the stuff that we're doing right now, we're because LSST so far it feels is perpetually almost ready to go. I was just looking at some of the forum posts, and they're like, yeah, we know that we keep saying it's soon and we're not giving you a date. We still don't know the date, but I keep hearing summer. I'm willing to believe it. I mean, they did their engineering data just, you know, not too long ago, you know, and then even with just that small amount of data, they were like, oops, here's 10,000 new asteroids. I mean, it's coming, and it's going to be big, and everything so far that they've been testing has been matching what the hype is essentially what's been going on. So I'm optimistic about it. So with that on the horizon, we want to grow and kind of get ourselves up and running, no pun intended, as soon as possible. Also, this is a volunteer organization, so there's no membership fees, there's no institution requirements. You know, you can be from a bigger place. I'm not going to care. It's a very open and welcoming environment. Just want to make that clear. So one of the big things that we're working on right now are starting up these materials that are Rubin focused and are going to be aimed at the specific undergraduate audience. This is inspired by both the Jupyter Notebook tutorials. How many here have looked at the Jupyter tutorials before? Yeah, not bad. Yeah, so one of the things that we've really appreciated so far is how well made those are. So we are, again, not wanting to reinvent the wheel. We are piggybacking off of their already good kind of upfront work that they've done to help people say, here's how you use the tools that go with Rubin and the LSST. But we want to have a little bit of extra wrapping that goes on top of that, which specifically can address some of the more what sometimes my students say are obvious or stupid questions, which they really are not, but it's just they're questions of people who don't have extensive background in this stuff. So a lot of times, especially for undergraduates, they may be a bit reticent in coming to people and saying, I have these questions, you know, because I think they're too basic. I don't want to ask my professor about this because I don't want him to say, well, duh, the answer is blah. So we want to have this kind of material out and say, look, you can get yourself up to speed and you don't necessarily have to quiz your mentor. We can take it from square one. That's okay. So this was inspired also by what was called the LSST Research Manual. It was a project that was done by a group of undergraduates out of Henry Ford College in Michigan. And I went to a Rubin community workshop. I saw a presentation that was done by Marie Fawaz. There's one of the authors. And I was just, this is exactly what I was envisioning is what is needed for Rubin. So we've been kind of, we took that idea and we're kind of running with it. So for example, the tutorials here, and this was intentionally done so, focus on the how to do data retrieval analysis with Rubin. So we want to focus a little bit more on the why. We want to give the scientific context to undergraduates who have not had a lot of previous experience, or this may be their first astronomy project. So we want to give them scientific context. We're trying to answer the, quote, obvious questions that they have. Also, we're going to integrate other non-astronomy specific resources that are still extremely useful, things like help with Python coding and that kind of stuff. Again, if it's not focused on Rubin specifically, we'll probably just be curating that stuff. We're going to find stuff that mentors of undergraduates say, hey, this works really well. We'll say, okay, good. We link it, right? And curating is what I mean. Say that. What I mean is instead of just saying, here, check out these links, and that's it. It's a little bit more targeted, a little bit more, okay, for this specific part, go to this part of the Python tutorial or something like that. Give them a little bit more direction because, again, if there's any level of students that need the most potential direction, it's on the undergraduate level. And then last one is suggesting potential project ideas, specifically projects for undergraduates because, again, unlike graduate students and postdocs, they may have an extremely narrow window. You know, the student comes to the professor and says, oh, I would like to do some astronomy research before I graduate. When do you graduate? In 3 months. Okay, well, I better go get something simple. So that's another thing that we want to have available are kind of these little package projects. It's nothing groundbreaking, but it doesn't need to be at the undergraduate level. We just want to give them a feeling of what this research kind of feels like. So give them something that is very self-closed. They can go through the whole thing in a relatively short amount of time. They're going to have the data to do it, whatever it is that the project is for. And be able to make suggestions about, like, here's about how long it'll probably take your student. Here's the products that you would expect from the project. So just as a throwing up some of the latest hot off the press stuff that we're working on, we have a couple of members who are working on creating what they call addendums to the Jupyter tutorials. So again, it's providing that background context, defining a lot of terms. But again, this is not to say that they couldn't find this stuff elsewhere, but we just want to put it all in one place. They don't have to go running all over the internet or for different resources. And also keep it in the same format as the Jupyter tutorials, so it all feels like one coherent thing when they're working through it. So like I said, we're still kind of revving up. We're collecting expertise, trying to decide on which projects we want to really focus our energy on as in these kind of last steps before the data actually gets unleashed. So we have what we're calling a Midwest meetup this year. It's kind of to be something like a sprint where we're going to specifically try to get as much of these tutorial addendums ready to go before the next Rubin Community Workshop, which is going to be at the end of July. So that's going to be in late May. It's confirmed at Monmouth College. We just don't have a specific date yet. But if you're curious, I can give you information on that as it becomes available. Also, we're starting to also look around and see what kind of financial support we can get for this kind of work. Because right now we're just completely all volunteer. So you can imagine it makes things a bit slower. But at the same time, we're hoping that if we can get a little bit of buy-in from institutions who are interested in promoting undergraduate research, then fingers crossed, maybe we can get a little bit of actual financial support. And then what I consider the most important thing right now is just getting the word out, because again, I continuously get paranoid that someone else somewhere in the country is doing this exact same thing. And then at some point we're going to realize that we just spent a whole lot of effort on that, where we're just kind of covering the same ground. So I just want to make sure that everyone in the country, as much as possible, knows about this organization, so they can let us know if someone is doing something that's very closely related to this and we just don't know about it yet. So if you're curious, join us, and very much so spread the word. Thanks to the LSST Discovery Alliance, we now do have an online presence, and we're really official because we have a GitHub. So we're putting new stuff up on there and making ourselves hopefully a little bit more visible that way. So, thank you very much.
Any questions?
Yeah.
I know I kind of mentioned this down the hallway, but
yeah,
probably the only thing that I missed about higher ed is mentoring student projects and research projects like this. And do they have anything that's equivalent for citizen science? I mean, I know they've got like things on Zoom and stuff like that, but like I could picture bringing in just some folks that are like really into action about and beyond some of these things and how to do it. Is there anything equivalent on the citizen science side?
Not that.
I'm not aware of anything. I know the Rubin or LSST program office is planning on some of that coming out of the education office. I think they're developing stuff like that.
Yeah, there's a couple of
we get
yeah, there's a couple of things
Yeah.
that they put out on Zoom first, but this is kind of like all what those are. That'd be fun.
I mean, it's kind of the closest stuff that you would get for citizen science, I think, because the level of complexity is pretty close between the two, especially for starting out undergraduates.
Okay. Mark, again.
Thank you.
What do I have to do to put a thumb drive on your computer? Just stick it in the hole and. And I will fake the start time.
You're going to give yourself extra time?
No, I'm going to give myself less time so that I don't run into Zoe's time.
So your drive is full there.
Oh, it's not.
Oh, you pressed on the wrong one.
No, this is what my drive does every time, because it interfaces with a Linux system, and Microsoft has a cow. It's down farther. JS 2026. That's it. Yeah. Okay, and that should work. Okay, well, you all have to suffer through me now. I'm Alan Smith. I'm at Austin Peay State University. One of my many hats I wear too many hats, by the way, is working on the mission design and ground-based calibration strategies for the Nancy Grace Roman Space Telescope. We tried to pick a long, incomprehensible title. We succeeded. So what are we doing? So, this is funding is provided by this. There's a NASA meatball on it. They actually give us money to do this. We are establishing SI traceable standard reference fields and type 1A supernova low redshift calibration for the Roman wide field science. So we're only looking at part of it, of all of everything Roman is doing. This particular project involves the National Institutes of Standards, APSU, and Yale. And it includes some funding for student training, not as much as was requested. And Allie will yell at me when I say something wrong, right? No? Okay. Mission itself, the Nancy Roman Grace Roman, we'll call it, is designed to be a 5-year NASA in-space mission with a 10-year lifetime goal. Maybe they'll beat that. It's going to be at the L2 orbit position. It's projected to launch out of Cape Canaveral, whatever they're calling themselves these days. It used to be the Air Force Station, but I think it's Space Force Delta something or other. Scheduled launch day right now is the 27th of September, and it's scheduled to go on a Falcon Heavy and operate at warm, basically, for an infrared mission. Okay. The telescope itself is the same size as Hubble, roughly. The mirror is 2.4 meter mirror. It has an imaging survey from, call it 0.5 down to 2.3 microns with 8 filters covering that band. It's got GRISM and PRISM spectroscopy, mostly, in the bands shown there. The PRISM or the GRISM is the top one, PRISM is the bottom one. And it's actually 4 surveys in one. It's kind of like the Ronco vegetable peeler television commercials at 2 a.m. Wait, there's more. We have the high latitude wide area survey, basically 5,000 square degrees, comparable to the dark energy survey. The high latitude domain survey, comparable to LSST or Rubin LSST, but in a smaller field. We have the galactic bulge time domain survey. You can guess where that is. And then we also support the science community. And we have already had, I think, the first selection for open call papers or projects. Okay. And there will be more. The specs, again, it's the size of the Hubble telescope, same sensitivity, but only 1/5 the weight. And this is one of the big things in space is you want to lightweight your mirrors as much as possible. This is what 35 years of additional technology does for you. Sensitivity and resolution the same, but the field of view is about 100 times larger than Hubble. And this will allow us to do 5,000 square degree surveys. And so it'll gather about 500 times faster. L3 Harris Technologies is the one is building the spacecraft bus, and are they doing the mirrors, or do you know? Oh, okay, ball. Oh, that's the most expensive part of the spacecraft then. Okay. This is, typical student. So the wide field imager, the wide field instrument itself is shown there. It is, you can read the word, but basically it's 18 different imaging detectors. Focal plane shutter over the top of it. This is an issue because it spans, oh my gosh, 18 arc minutes from side to side. That is a huge angular change in space, and we are going crazy trying to figure out how much the band passes shift from the center to the edge and how much distortion there is in there. So each area is going to be roughly the size of each image will capture an area roughly the size of the full moon, maybe a little bit bigger. And 50 times, it's going to cover 50 times as much sky as Hubble did in the first 30 years, combined. So basically, we open the shutter once, and we've got a Hubble data or a Hubble volume worth of data in terms of aerial coverage, not in terms of depth. Field size comparison shows you the Roman field of view versus Hubble, both the ACS and WIF-PIC3 or WIF-C3, and near KAM on JW. And the filter curves are the 8 filters and GRISM passes where we have those filters there's the prism, let's see, which is which? Took one of my labels off. The prism is the top dash line, the prism is the lower dash line, and there is a wideband filter that comes up there and comes down over here. That spans. So it's basically standard filters plus an H plus K H plus K and an I plus J filter. I hate infrared filters. We have to calibrate this. And I use this picture because, hey, why not? It's got a cat in it. So the calibration team is the cat approaching the universe. And the universe is going to teach us a new thing or two about what you're looking at, because this cat obviously doesn't know what's going on. All right, so calibration, we're only focusing on ensuring the wide field infrared instrument, or the wide field instrument is actually gets data. And it's even worse than that. We're doing ground-based calibration for a space-based instrument. There's an onboard, on-orbit calibration team. They don't talk to us. We don't talk to them, except we do. We pass data back and forth in theory. We do. We're doing that. We are developing reference fields, which are in the continuous viewing zone. This is near the ecliptic poles. And this is so that the on-orbit team can actually scan those fields and say a priori, or hopefully a priori, hey, we know this is a K giant star, or this is a white dwarf, or this is a fuzzy thing. What do they call this? Oh, galaxies. And we're going to do that. We're focusing on the stellar component because if you deal with galaxies, anybody deal with galaxies in here? You know there is no such thing as a standard galaxy, right? That sounded like derision. I mean, when I was a graduate student, way back when, I was young, what star people were talking 2 or 3 hundredths of a magnitude precision across the sky. That was great. LSST and DES and all have shown we can actually do 3 millimags across the sky, end to end. Galaxy people are now actively saying, oh, we're at 15% uncertainty, without laughing. When I was a student, 35% was a good value for galaxies. That was back a while. Anyway, so we're going to do some of this from space, some from the ground. The group I'm working with is doing it from the ground primarily. And this is mostly to be used as spacecraft and detector health monitoring. Because, hey, we have unlimited time. Well, we don't, but we have time. And the goal is we will scan a couple of patches, determine what's in them, characterize the spectral energy distribution of the stars, the magnitudes, all that stuff. And then the galaxy or the spacecraft can scan across it as it moves from one place to another once they're in operation, or go there and sit there and say, hey, yeah, you moron, you didn't do it right, which is probably the case. Why is this important? Are you going to talk about the ice? Okay, this is important because in thermal vacuum, the spacecraft is out of thermal vacuum. They notice, hey, there's water vapor inside the camera. And water vapor in a vacuum of space, where it's cold, turns to ice. And my first question is, oh, you're just out of thermal vac, you're still on the ground. You're going to open it up and evacuate it, right? Nope, the camera's sealed. So we have an ice patch that is going to form and move periodically based on heat. And we need to know where that is and how it's behaving. So these are some of the fields we're looking at. We're doing both photometric, spectroscopic, and astrometric monitoring. Astrometry, I don't know jack about astrometry other than I think I spelled it correctly there twice. But we're looking primarily at photometry and spectroscopy. We're looking at the Euclid Deep North Field. This is essentially the north ecliptic pole region. The Kepler fields, and of course, the spacecraft picked the one region I don't have any data in. I've been watching the Kepler field for 20 years, and they picked the one region I don't have data We're looking at M44 as a possible one, and then Stripe 82 because it gives us a tie to the southern hemisphere, so we can make sure everything ties together as we move hemispheres. It should. There's no atmosphere in space, in theory. And then we're also looking at deep supernova fields, which of course are chosen so they do not overlap with the dark energy survey deep supernova fields. Okay. So photometric reference for selection, we have an ongoing observing program to characterize a couple of fields. And Zoe in the next talk is going to show you initial work from the one or three. Yeah, she's going to show you from one of the North Ecliptic Pole field. I'll let her explain what she's doing. So we've been doing this with the National Undergraduate Research Observatory, which is a 1.04 meter telescope at Lowell Observatory in Flagstaff. We are looking at follow-up of what's in there with the IRTF to get infrared imaging and spectroscopy, CTIO 0.9 meter in the south, and SOAR follow-up to get optical photometry or optical spectroscopy, and then Gemini north and south to get deep high resolution spectra field. So for imaging observations, if we have non-photometric weather, then we're looking for variable stars because that's what everybody does, right? And if it's photometric weather, then we are looking at identifying rough spectral classes of stars with the small aperture telescopes, and we're using Brian Yanni's data from the paper in 2009. I'll show you a picture in a second. And the transformations from Megan Porter, who was one of my students, this is her senior thesis last year. And she's looking at photometric transformations to the LSST data system set. And this is now in, if you need it, RTN 99 on the LSST website. And Megan is now pursuing a, what do you call that thing? PhD, that's it. But she's gone to the dark side. She's looking at galaxies and black holes. All right. Photometric reference selection. It's usually what cats do. And so this is, I think, what Zoe is going to talk about if I'm just saying, hey, here's a slide. But the Yanni et al. Paper in 2009 in Sloan colors, and that's one of the reasons why I'm using Sloan filters for this, gave us that model. On the right is data from our first reference or our first attempt at doing anything. The stuff in magenta labeled K giant is the color space the K giant should be in. Everything in there with a magenta dot needs a spectrum. And this is hence the need for the spectroscopic follow-up work. And we also need to go deeper because this does not go very deep data-wise. Next, we're going to revisit the EDF North this May and begin the Roman Kepler field. And then we need to go to bigger and better because everything is always better when you get bigger and better. Any questions? Seeing no questions. Yes.
A general Roman related question. In terms of the way that the sensors are arranged,
Yeah.
do you know why they're arranged like that?
No. I was not on the instrument design team because they want it to work. I do not know why they picked that arrangement. I really don't. Other than if you look at the design, the spacecraft documentation, they have the way they tile and mosaic, moving around to get interstitial spaces and sliding over half a space, doing sort of like the dark energy survey. You can map it so many ways and get full coverage. And it's just designed to cover everything with maximum number of observations per star with minimum number of visits. Right? Huh?
I think so. I wasn't there for that part.
She's the expert in it. Anyway, any other questions?
Depending on asked it,
Oh.
all your cats.
This one is my cat. The other one, the others in there are, things found on web. But this was Thumper when he was a wee little kitten and had all 4 legs. He's down to 3 legs now. So our next speaker. What's his name?
You're good.
Oh, okay.
No, you're good.
Our next speaker is Zoe Wolf from Austin Peay State University, who's going to talk about the stuff I screwed up.
HDMI or USB-C?
Both, but HDMI works. Ooh.
And are you on the Zoom call?
Where's the button to press share my screen?
Um,
Oh, share screen.
click entire screen.
Thanks.
Then make sure. Did you give her the?
Yeah. Do you want timing until the whole thing ends or the 12 minutes for your talk?
The 12 minutes, please.
Can you mute the mic on your Zoom?
That.
It's muted.
I already
Maybe
have it on.
mute your speakers. Try talking now.
Talking now?
Good.
Awesome.
There was some feedback there.
Okay. There we go. Hello, everyone. My name is Zoe Wolf. I'm a junior undergraduate at Austin Peay State University, and I'm going to tell you about ground calibrations for Nancy Grace Roman detector health. So first, we're going to talk about identifying the fields. Probably breeze past those because Dr. Smith talked about that a lot. The data that we collected and the data that's missing. Also, we were funded by that grant, NASA, and the Tennessee Space Grant Consortium. So identifying the fields. What we imaged was the Euclid Deep Field North, and here's an image of it. So the 3 stars are 3 white dwarfs that were in the center of each of our images. From left to right, it's white dwarf 1, white dwarf 2, white dwarf 3. So where is the Euclid Deep Field North? It is very close to the North Ecliptic Pole. It's in the constellation Draco, the Dragon. How big is it? It's 22.9 square degrees. Why this field? I am glad you asked. We chose it for a simple reason because it was up in the sky. We could image it. It's timing. It was time to observe it. And why white dwarfs? Why do we care about the white dwarfs? Why did we image them for this project? We chose them because we understand their atmospheres. All of these white dwarfs are hydrogen atmospheres, so they're relatively simple to model. Also, from those models, we can derive their spectra, which can tell us about their effective temperatures and so much more. And my favorite part, when and where did we image it? This gets to our data in hand, and that involved an observing ground in Flagstaff, Arizona, at Lowell Observatory's 42-inch Hall telescope, which is run by the National Undergraduate Research Observatory. And that's me and a classmate that went and collected the data. So catalog information. We collected the data, and then we used IRAF to process it. We would have used Python if Dr. Smith wasn't so old and ancient. I got his permission to say that. So once we processed it, we were able to use TopCat to cross-match it. And I discovered that I love TopCat because we were able to cross-match with all these different surveys. So we used White Dwarf Field 2, so the second star you saw in the picture back then, and we cross-matched it with as many surveys as possible that were available in TopCat. So one of them was the 2-mass survey, and I have a plot that I was very happy with. So the red dots are the cross matches. So the stellar content of our white dwarf field 2 matched with what's in 2-mass. So what's in 2-mass, what was in 2-mass was in our field, and that's what that is showing. There were 1,049 matches, which was to be expected because of the location in the galactic plane. And then with all of the relevant catalogs that we cross-matched with, there was an average of 1,327 matches. And relevant catalogs, I thought y'all might ask. So those included things, as you can read there, such as SDSS, Gaia DR3, some Galex, some all-wise, some unwise. There's a lot of wise. But anyways, those were selected for if they had spectra or not, their astrometry, and if their astrometry was based on Gaia DR2. If it was based on Gaia Data Release 2, I'm getting the numbers right. Yes, then I didn't consider it because Gaia Data Release 3 is more up to date. So what is missing? I'm glad you asked again. So the information that is missing is the magenta dots, essentially. And you may remember that this slide was in Dr. Smith's slides. And so this looks good because it matches Yanni's paper. And then what's special about those magenta dots is that we're hoping that there will be K-giants in that area. Now, why K-giants? Because they make for good calibrators. They will be our calibrators for this, for what we're doing. And what's missing is we need the spectra to find out which ones of those magenta stars or dots are the K-giants. And we expect 5 to 10% of them to be K-giants, which that is why we need the spectra. And the information that's missing will shape our future proposals. So proposals to IRTF, SOAR, Gemini. Thank you. Questions? Yes. What makes them good calibrators? It's because we can see them from long distances away, and they're generally not variable. Any other questions?
Dr. Smith, is it a requirement that you like cats if you're going to be his student?
That is my cat. Yes.
Strongly involved.
I spent 30 minutes this morning finding just the right picture.
Heavily written K-giants are really good revenue sources in all of Landing's catalog on their own. Any other questions for Zoe? Oh, come on. Come on.
I won't bite.
Okay.
Okay.
Thank our speakers. Wrap everything up. I'm getting old.
Okay, I think we can finish this.
I think so. Yep. So anybody online, we'll see you again in the morning at 9:30 a.m.